Okay, I'm gonna pass back your homework one at some point here. I entered the scores there in Blackboard, and so if your score was low, you know, this is not something to freak out about. Because for one thing, that's just a small percentage of your overall grade. But just look upon that as an opportunity to show improvements in the future, right? Okay, so at least you have again, an opportunity to do better by, and you might do that by maybe spending a little bit more time with the problems, if that time is available to you, or in particular coming to my office and talk to me and ask questions about the problems, right? If you don't understand how to do a problem, so you don't have a lot of additional places where you can go to seek help other than your classmates or myself, right? So try to take advantage of those opportunities. If you trying to improve your homework scores. Now, if for some of you, even though your raw score was maybe a little bit low, because you really had just by what you had written. You had demonstrated that you had put a lot of effort into the questions, right, into answering the questions. Then, or at least it appeared that you had put a lot of effort into answering the questions. Then I curved some of the scores up as sort of a bonus there, right, for your efforts, because these are sometimes tricky problems, right, and sometimes you just don't see the key to the solution, right? It's just there's some little trick maybe there that you didn't stumble upon. So, but you put a lot of effort into it. So, and you're learning from that effort. So that's good. On the other hand, if you didn't score very high, but then I just had sort of minimal answers written down, or responses to the questions written down, then I didn't feel like I should curb the score. But again, just look upon that as an opportunity to do better on the later homeworks or on the test. So on your future homeworks, come to visit me, right? If you have questions about, or talk to your classmates if you have questions about some of the problems, right? Okay. We postponed the test, but I didn't make this announcement in Blackboard. So, but it's next Wednesday, so it's a week from today. So I put it off by a week. But and I want to get through, as we won't be able to get through remember, I posted the fourth homework. We're not going to get through the fourth homework by that test. So that means the test design on my part is going to be a little bit tricky, because I've got to ask, try to ask questions that I think you can do, but I don't want them to be just boring, trivial questions either. So because that won't be any fun. So, well, anyway, that's my problem to think about. But I want to get through as many examples as I can today, and hopefully at least introduce the final set models that we really use, that we rely on heavily for counting. Okay, although again, not every problem is going to fit perfectly into a set model, but vice versa. Not every problem can be solved with the algorithmic approach either, right? So you have to have a mixture of them. But I do have to show you at least what the basic set models are, right? So maybe we can get through those today, and then on Monday we'll have a chance to solve some more problems. So you'll have a better background for the test on Wednesday. So we can maybe look at questions from homework 3 or questions from the sample test. But until you've really had a chance to grapple with some of these questions on your own, you really cannot absorb it. It's not something that people can tell you. You have to see examples, but the examples are not sufficient. Until you've worked on the problems yourself, you're not going to really sort of construct your knowledge of how to do these counting problems. So anyway, but that's true of any subject, so not just combinatorics. But the fun thing about combinatorics is, just like in this problem, in almost all these problems, right? It doesn't require you don't have to have a lot of technical knowledge, right? So it doesn't require a lot of preparation, right, to understand and solve these problems. We do need to have seen a few set models and seen a few examples, right? But with just armed with that little bit, you can really attack almost any of these problems. So that's why these are such great combinatorics, such great source of puzzles, right? Right. Okay. So it's sometimes just you and your logic, right? Battling with the problem. Okay. So well, let's continue here. So we left with this problem last time. How many 5-digit integers? I'm going to assume that there's not going to be repetition, but it's not really clear from the instructions here. So how many 5-digit integers can be constructed from these 5 digits exactly? Okay, so just these 5. All right, so arranged in some order, right? Okay, to get exactly a 5-digit integer. So for instance, no repetition. So we wouldn't have 3, 3, 3, 3, 3, 3, right, as a possibility. I'm going to eliminate that, but that's not really clear from the description there. Okay. All right. So there's the question. Okay. This would be made a lot easier, right, if these ones here were distinguishable from one another, but all ones tend to look alike, correct? Okay. So that's really the issue with the problem. Suppose that I distinguish the ones here, right? So let's put a superscript here so that I can distinguish these 3 digits, right? So I'm going to call that 1A and this 1B and this 1C, right? Okay. So if you can distinguish between the 1 digits, then I think that makes the problem a lot easier. Can you describe for me a solution to this problem? I think an algorithmic solution would be kind of obvious here. What would be an algorithm for building the 5-digit number? It would be like 5 factorial, right? But how did you arrive at that, Dalton?
First choice, you have 5 options since the ones are different. Second choice, you have 4 options. Next, you have 3, 2.
Yeah, so Dalton is just saying, I'm just going to build we would just build there, right, we would just build a 5-digit integer, right, from left to right, just by picking the digits, right? So when you pick the first digit, correct, on the left, you would have 5 choices, correct, right? And then when you pick the second digit, you would have then 4 remaining choices, right, if I'm not going to have repetition. And then third digit, you would have, is it 3 choices, right, okay? And so forth, right, okay? So it's easy to describe an algorithm in that case, right, for building the integer, and you know how many choices you have at each decision point in the algorithm, correct, right? So if S here is if we let S there be the set of integers, right, then it looks like the cardinality of S, right, based on that algorithm would be, as Dalton mentioned there, right, you've got, if you're going to build the number from left to right, you've got 5 choices, right, for the first digit, right, and 4 choices for the second, and 3 choices for the third, and then, of course, when you get to the last digit, well, you only have 1 choice there, right, because all the other digits have been used up, right, so you just get 5 times 4 times 3 times 2 times 1. Does that make sense, right? Okay, so that I think is 120, is that right? All right, so oh, by the way, now, you're going to notice in the solutions to the homework, I don't often actually bother to calculate the final number here, okay? So I will show you the computation to compute the answer, but I often don't go through the computation. So, but you can do that, okay, yourself there in the homework solutions. All right, now, but let's actually execute that algorithm then, right? Okay, so let's actually do this. So you guys help me with this. So we're going to choose so let's actually build an integer here, right, which is going to be an element of this set, right? So we make our first choice. What do y'all want for the first one there? 1C. Okay, right. So 1C, and then what next there? Kaylee? 8, and then 1B, all right, and then what? 1A, right, and then what's left? 3? Okay, yeah. So there's one of the sequences, right, that we would generate from that particular algorithm. Okay. However, a slightly different sequence, right, would be this one, and that is counted differently by this algorithm, right? Okay. Because we didn't make the same sequence of choices there, right? Here I started with 1B rather than 1C, still picked 8 second, right? But in the third place, I picked 1A rather than 1B, right? Okay. So by our algorithms counting, this and this sequence are different because I made different choices, right, at different places in the algorithm. Well, okay, so again, with the superscripts on the letters, indeed, right, this is a different number, quote unquote, right, okay? It's a different sequence of the digits. But of course, in practice, right, we usually don't label our digits 1, correct, when we put them into a number. So in practice, these two numbers are the same, right, okay? They're both 18,113, right? Okay, so in the actual description of this problem, we have overcounted, right? Okay, because these two ways of executing the algorithm were different, but they led to the same result. Okay, so the 120 is going to be bigger than the actual value, right? Okay, the actual set of, it's not set of integers there, but set of, well, I guess it is five digit integers, right? Okay. All right, so this is a problem now that it's going to be pestering us now all along, okay, in counting problems, is these items, right, that we're arranging to build these integers, they're not distinguishable from one another, okay? Ones, as I mentioned, all tend to look alike, correct, right, okay? So, and so we have to account for that in our counting, and that causes us all sorts of issues, all right? So that really complicates counting problems. Well, sometimes it simplifies them, okay? But more often it will complicate them, okay? So, so here's the thing. How are we going to count, right? Okay. So can we think of another way there of counting this set of integers where it really doesn't matter now that the ones are indistinguishable from one another? Okay. I can think of a couple of ways to approach this. All right, but do y'all have any ideas there on what we might do? One thing we might do, since we've already counted the 120, all right, okay, with labeling the letters, we might think about how we can, working from this set, how we can reduce the size of this set to the proper number, right? Okay, so we might think, how many of these sort of duplications do we have, right? How can I account for those duplications? So that's one way to approach the problem, which is kind of attractive in this case, since we've already counted the 120, right? Okay, so it's a matter of just reducing that 120 properly. Or you might think of a completely different algorithm for building the 5-digit integer. All right. So any suggestions there on what we might try? Yeah, Sean. Mm-hmm.
So for the first digit, we actually only have 3 choices.
Yeah, well, I don't know how to answer that. Yeah, it's yes and no. That's the tricky part about the problem, right? Okay. In a sense, you only have 3 choices because it's got to be a 1, a 3, or an 8. You're right, okay? But in another sense, you do have 3 choices because there's 3 of those ones, right? Okay. So, for instance, you can't say if I picked a 1 in the first number, I cannot pick a 1 again, right? Okay. That's normally what you would hope for, right? Okay, when you're not repeating the digits, but we don't have that luxury in this problem. So it's kind of, you're kind of correct, but. But where were you going with that?
I was going to say, so like for the first digit, it's you only get 3 choices. In the second digit, you still only have 3 choices.
Okay. Yeah, see, it's really, yeah, so this is where this is where you're, again, right, it's just, as I mentioned, these combinatorics problems, right, are it's just you and your logic, right, kind of fighting that simple problem, right, okay? The computations are not the issue here, right? We all know how to multiply and add, okay? Well, sometimes the multiplications are really large, though, right? Sometimes the answer to these are really large numbers, but it's not the arithmetic that's the issue here, right? We're not doing calculus, correct? Okay, it's just pure sort of reasoning, right? To think about this. Yes.
Could it be said that every single number is going to involve 3 ones, right? So is every single number going to have a duplicate?
Okay, so that's a good thing to think of, right? Okay, so you might be thinking about how many ways did I generate 18,113, okay, right, when I had the digits labeled. How many ways, how many of those sequences, right, with the labeled digits really result in the same value, correct? Okay, so we saw 2 of them. Well, I forgot what they were, though. What did you say? Do you remember, Kaylee, what you told me here? Really doesn't matter. I can put them anyway. C. And then I mixed it up and said, who cares, right? This is A, and this is B, and this is C. All right. So those two sequences of choices both result in 18,113. So let's think. What other sequence of choices also would result in 18,113?
1B.
Yeah, 1B what? 8.
1C.
1C. And 1A, right? And then a 3. Is there another one? There should be 6 of them. Oh, Kaylee, that's good, right? Why 6? So why should there really be 6 of these things? So we got 3 of them, but why should there really be 6? But it's 3 factorial. So we keep using the term factorial, so I've got to define that, okay, for people in the class that most people are familiar with that, right? But I'm going to define that soon, all right? But so it's 3 factorial, which is 3 times 2 times 1, right? How did you arrive at 3 times 2 times 1, which is 6? So how did you realize that there were going to be 6 of these sequences that all are 18,113?
So you already know that the second digit has to be 8 and the last digit has to be 3.
Right.
And the rest are filled with 1s. But,
The rest are filled with 1s, right.
You have 3 choices for which subscript to pick for the first place.
Oh, you said that so nicely, right, okay. All right, so here's what Kaylee is saying, right, okay. To generate 18,113, right, okay, that particular number, you know this is going to be 8 and this is going to be 3, right. So the only real question is how do we fill in the 1s, right, okay. Any rearrangement of the 1s, right, would also, as long as the 8 is here and the 3 is here, any rearrangement of the 1s will still give us 18,113. How many ways, then, can we rearrange the 1s? It's just how many arrangements of these 3 symbols do we have, right? Okay, so what Kaylee says, well, to line up the 3 1s, right, okay, in the number, well, let's see, I've got to pick the first one, right? How many choices do I have for the first one? 3, right? How many choices do I have for the second one? 2. How many choices do I have for the last one then? 1, right. So there's 3 times 2 times 1 ways of rearranging the 1s in this number. Does that make sense, Sean? Yeah, okay. So that means I didn't write them all down, but there are going to be 6 of these, right? Numbers that correspond to 18,113. Does that occur for every then? Does that occur for every then number in this list of these 120? Yeah, it does, right, okay, yeah. For every one of these 120 sequences, right, you can rearrange the 1s, right, in 6 ways, and you'll still have the same number there written, right? So the correct answer here for S is not this, but it's this divided by what? 6, right, okay? So what we really want to do is take the 5 times 4 times 3 times 2 times 1, right, and divide it by 6, okay? Which, by the way, remember, was 3 times 2 times 1, right? Okay, that's where that came from. So you really just get here 5 times 4, which is 20. So there's the there's one way of thinking about the problem, okay? Ooh, I like that, okay? Does that make sense, Eduardo? Yeah, okay. All right.
That's what I was going for.
Did you did you know there were 6 or 6 way of rearranging the ones?
I thought maybe like 5.
Okay, yeah, but yeah, now you know there's 6, right? So that's its own counting problem, okay? How many ways can I rearrange the ones? That's its own counting problem. But if you think about it as a counting problem, you'll soon deduce it's 3 times 2 times 1, right, okay? Now, is there another way that I can arrive at the 20, which remember, that was really 5 times 4. So is there another way that I could realize that the answer here was 5 times 4 in a little bit more direct fashion? Yeah, there is, okay? But this is the beauty, but also the difficulty, again, of these combinatorics problems, right, okay? You have to have some approach, some way of thinking about either modeling the set or some algorithm for building the set, right, okay, in order to count the set. Here's the second way of thinking about this. Look, you get a little bit of a, you can raise your hand. Did you have a suggestion?
Yeah, would it just be like you have 5 places to put the 8 and then 4 places to put the 3?
Exactly right, okay. Another way of thinking about this is what's really kind of key here, if you sort of flip your perspective, is where do I put the 8 and where do I put the 3, right? Okay? Because once the 8 and the 3 are placed, then you've got to fill the rest of it in with 1s because that's all you've got left, right? So once you've decided where to put the 8 and where to put the 3, the number is determined, correct? Because 1s are going to go everywhere else, right? Okay? So there's a great way of thinking of it. And how many places do you have to put the 8? 5, right, okay? And then once you place the 8, how many places do you have to put the 3? 4, right, in a 5-digit number, correct, right? So, so there's another way of realizing the answer is really 5 times 4, right? Where do we put the 8 or the 3? You can, think of that either way, right? And then where do we put the other digit once we placed the first one, right? Okay. The 5 and the 4 representing, right, the positions in the digit, correct? The positions in the digit. Because there are 5 of them, we know. So there's another way to arrive at the 5 times 4. Place the 8. And then place the 3. Beautiful. Okay, now, here's the harder version of the problem. What if you've got those 10 digits, is that 10? Yeah. And you want to form a 10-digit number from those 10 digits, okay? So, see, that really just magnifies the difficulty, right, okay? Because now you're no longer just dealing with duplicate 1s, but now you've also got duplicate 3s and duplicate 8s to worry about, right, okay? So, same problem, but we've really just bumped up the order of difficulty, right, okay? I think y'all could think about that, but let's defer that problem till later, because we're going to have a set model that will help us with this problem, okay? So we don't have to think about the problem algorithmically, interestingly, all right? We have a set model to help us with that one. Okay, all right, so here's what we've been, all right, so finally, here is another set model, okay? So we've been really using this set model indirectly in a lot of these problems in these notes, okay? Because a lot of these problems involved arranging objects into a list, right, okay, from left to right, just like we were doing in that prior problem. And so we have a model for arranging a set into a list, okay? So suppose you have a positive integer, r, okay? And then you have a set S of cardinality n. The book doesn't make the restriction that n has to be positive, but it's kind of silly if your set is empty, okay? So I'm going to insist that your set be non-empty. It has to have at least one element in it, all right? Now, but one important note here, the R has to be less than or equal to the N, okay? All right? An R permutation of of elements from the set S, that means an ordered arrangement of R elements. Not necessarily all the elements of the set, right? But it's an ordered arrangement of R elements taken out of the set. But it's an ordered arrangement, so they are ordered from left to right, okay? So if you've got a set and you take some elements out of the set, doesn't have to be the whole set, but you take some elements out of the set, and then you arrange those elements from left to right in an order. So by the way, this means that the elements of the set have to be, you have to be able to distinguish them, right? Okay, but that's a characteristic of sets anyway. All right, you have to be able to distinguish elements in a set. You don't have duplicate elements in a set. So that's called an R permutation of the set. Okay, and ordered arrangements occur frequently when we're counting sets. So this is a very useful. This is going to be a very useful set model for us because these sorts of arrangements come up frequently in counting problems. All right. So here's the important theorem, which I think you're already familiar with. All right. So if you have a set, right? Okay. And then you look at the set of all R permutations, the set of all R permutations taken from that set, right? Okay. So an R permutation is a single list, but if you look at the set of all R permutations, here's how you can count that. Okay. And well, you count it like this, right? It's just going to be n. That's the number of elements in the set, right? Minus times n minus 1 times n minus 2 down to n minus r plus 1. And we denote that product in the book by using this notation, PNR. But I'm going to point out something about this notation. All right, let me show you. Now that product is kind of clumsy, right? Because it involves a lot of factors. So again, this is our notation for that product. But here's another way of expressing that product that involves a little bit less of those factors. Okay, so you can also express this product as this quotient. This numerator is read n factorial, and n factorial is an operation. All right, and so r factorial is same operation. This is an operation that we perform with integers, and here's how it's defined. Okay, so by definition, k factorial means this product. Okay, it's just shorthand for this product. So whenever you see factorial, remember that is product. Okay, and you're only going to apply that to non-negative integers. Only going to apply that to non-negative integers because this definition only makes sense for non-negative integers. But the concept of a factorial you can actually generalize to numbers in general, not just integers. But this definition only applies for non-negative integers, okay? So you see how the product is formed. It's k times k minus 1 times k minus 2 all the way down to 1. Of course, you can really leave off the 1 because that's kind of superfluous, but we usually just include it in the definition just to make the pattern more explicit, right? Now, 0 factorial does not quite fit this definition, right? But 0 factorial is defined. So by definition, that is 1, okay? So whenever you see 0 factorial, you can just immediately replace that by 1. It's like raising a number to the 0th power is also 1, right? Okay, well, 0 factorial is by definition 1. And the reason we use that definition is because it's going to make some of our formulas work out nicely, all right? Well, in particular, I'm going to make this equation, or this fraction, defined in more cases, all right? So if you're taking a permutation of the entire set, so if r is equal to n, right? If r is equal to n, Oh, I did this wrong, I think. Sorry, this is n minus r factorial, okay? Whoops. So if you're taking a permutation of the entire set, that means you're going to take everything out of the set and you're going to put those, you're going to arrange those elements in order from left to right, okay? You're going to put them into a list, right? An ordered arrangement from left to right. Then the number of those ordered arrangements is going to be, since r would be the same as n, you would have n factorial over 0 factorial. But what's 0 factorial? 1. So you just get n factorial, okay? So it would be n times n minus 1 times n minus 2 times n minus 3, etc., all the way down to 1. That would be the number of ways of ordering, listing all the elements out of a set from left to right, okay, if the set is of size n. Now, one thing I want to point out here, though, is this actually, in this definition, this notation represents a number, right? That represents the number of R permutations. But I often use that to actually represent the set of R permutations. So technically this is a value, but I often use this to represent a set, not the size of the set. So by set, I mean the set of R permutations of this integer segment, okay? So I will frequently use this as a set rather than as a cardinality of a set, okay? So I just want to point that out because it's going to come up in problems and in solutions to problems. All right, well, let's apply this definition. It's very easy to apply. So for simple counting problems, very easy to apply. So how many four-letter words can be formed from the vowels, okay? So the vowels are, what are the vowels there? A, E, I, O, and U, right, okay? So we want to form a four-letter word from A, E, I, O, and U. But now notice that there's no restrictions there on repetition, right, okay? So you can repeat vowels in this part A. You can repeat a vowel, right? But it's still got to be a four-letter word formed from A, E, I, O, or U, okay? So, well, how many words is that going to be? Well, how can you form such a word? So what's an algorithm for creating a four-letter word from the vowels? Let's call S here the set of words. Who was going to say something?
So you have 5 vowels to choose from?
Yeah, you have 5 vowels to choose from. When you're forming a four-letter word, you're just going to, I guess, right, go from left to right and pick letters, correct, to form the word, right, okay? Notice I've got word in quotes, so it doesn't have to be a word in any language, right? It just has to be a string of 4 vowels, okay? So so you just go from left to right and pick letters, correct? So how many choices do you have for the first letter? In your 5, right, okay? And how many do you have for the second letter? 5, right, because we're allowing repetition, right, okay? So this is easy to count, correct? So you have 5 choices to make the first letter, 5 choices for the second, how many for the third? 5, right? And for the fourth, it's also 5, right? So the cardinality here is clearly, of this set, is clearly 5 to the 4th power, right? Okay? What's our set model there? So we didn't write down the set model explicitly, right? But if you wanted to solve this through a model, what would be your model? So what does S correspond to? Yes, the integer segment? Yeah, so you're thinking of the integer segment, right? And what are you doing with the integer segment? You're raising it to the power 4. You're going to form a cross product, right? This with itself as a factor 4 times, correct? And again, our notation for that is we can write that cross product, right, as this integer segment raised to the fourth power. And again, why is that really a set model? Because what do things in here look like? So what are in cross products? Not ordered pairs in this case, but ordered what? Tuples, right. What kind of tuple here? No, not a 5-tuple. This is a quadruple, right? This is a 4-tuple, right? Okay, because you've got 4 factors in your cross product. What does a 4-tuple in there look like as an example? Give me a sample 4-tuple there out of 5 to the 4th power. Not going to have A's. These are numbers. What? 1. You're going to make all 1s there? Oh, right. Okay, sure, right. Okay, so there's 1. What word does that, what word could you think of that as matching? 4 A's, right, okay. Yeah, you're implicitly assuming in that case that the number 1 is matched to what letter? A, right, which is probably what you would do, right, in alphabetical order? Right, okay. So that tuple matches that word, right, okay. And so that's why, so you can easily see what word every tuple is going to match, right, is going to correspond to, right. So this is why there's a correspondence between S and this particular cross product. But we know what the size of this cross product is, right? It's what? It's that, correct? Okay, it's 5 to the 4th power, right? Okay, so so you still get 5 to the 4th power, whatever that. What's 5 to the 4th power? 625? Yeah, okay. So there's 625 of these 4-letter words. Now, but what if you don't allow repetition, right? So what if you're restricted to not repeating a letter? Okay, so still vowels, but not repeating a letter. Then what's the set model going to be? So, all right, so in this case, Sean is saying, I know that S is going to be... right. Well, okay, it's 5 times 4 times 3 times 2, right? Okay, which is indeed 5 factorial. The 1 there is irrelevant, correct? Okay, so so you're right, correct. This is 5 factorial is the size there. That's what, 120, right? Okay. So, of course, that's a lot fewer words, right, okay, than here, which was 625. But that, so, but not Sean, but Dalton, you're giving me kind of an algorithmic approach here, right, okay? Algorithmically, how would you be building these words in this case?
First letter you have 5 choices.
Yeah, first letter you have 5 choices, second letter you have... Because you cannot repeat, right? Yeah, 3 and then 2, right, okay? So it's easy to see that 5 times 4 times 3 times 2 is the answer, right, okay? Which happens to be 5 factorial because the 1 factor is meaningless, right? So it's easy to see that 120 is the correct answer. That's algorithmically. But if I wanted to use a set model, right, so if I explicitly said, show me a set model in this case that corresponds to S, what would the set be? Okay, so what set corresponds to S? Okay, well, what have you done in, what do these words look like here? Okay, they are ordered arrangements, right, of different letters, right? How many letters have you picked? 4, right, from the set of what? 5 letters, the set of vowels, correct, right? So you've taken 4 letters out of your 5-letter set of vowels, right? And then you've put those in order. What is that thing called? When you take items from a set and then arrange them from left to right. Not a tuple. A permutation, right. That is a permutation, okay? Right, that's a set, that's a permutation. Right, okay? So anytime you have a big set and you take some elements out of the set and write them in order, the order is important, that is, oh, I see why you're using tuple there. Okay, who said tuple? It kind of is a tuple, but, yeah, but, yeah, all right. It kind of is a tuple because they're written in order. But anytime you take anytime you have a big set and you take some items out of the set and put them in order, that is called a permutation. In this case now, what's the size of the, what type of permutation is this? Well, how many items did we pick? 4. So so our words are 4 permutations from the set of vowels, okay? There are 4 permutations from the set of vowels. Shall I say that right? Okay. So a word here, quote unquote, right, is a 4 permutation, because we've picked 4 of the vowels, right? From is a 4 permutation from the set of vowels. Which, of course, is this set, right? So that's what a single word is, right? That's what a single word is. But then S is what? The set of what? Actually, it doesn't correspond to. Really, S is literally equal to what? The set of all 4 permutations, right? From the set of vowels, okay? That really is what S is. That's not a model for S. That is S, okay? It's the set of all 4 permutations, right, from the set of vowels, yeah.
So this is where we'll use Theorem 8, so
Yes, this is...
4 and N is 5?
That's exactly right, okay? So that's what I was getting to here. So S is the set of all 4 permutations, right? Again, from the set of vowels. I should have given that a name earlier, but I didn't have that much foresight, okay? So that's literally what, that's not a model for S, that's literally what S is, okay? And now, Kayla, you said, right? So now we can count S, right? In a slightly different way by using Theorem 8, right? Because Theorem 8 tells us how many of these 4 permutations there are, right? So according to that theorem, what? That would be what? 5 factorial, right? Because that's the size of the set of vowels divided by what? 5 minus 4, right? Factorial? Yeah, okay, because we're taking 4 permutations from S. Well, 5 minus 4 factorial is 1 factorial, which is 1. So you end up getting, again, 5 factorial here, right? There's just another way of counting that. So again, whenever you're arranging items from a set, almost certainly you are building permutations, okay? You're dealing with a set of permutations. Not always, but maybe always, okay? 99% of the time. Now, okay, this is what S is exactly, right? This is what S is exactly. But a real model for S would instead be, instead of thinking of the set of 4 permutations from the set of vowels, you could also think of the set of 4 permutations from what set that's a convenient substitute for the set of vowels. What did we use earlier? Yeah, we just use that integer segment, right, okay? So that I don't have to be constantly having to write out, the set of vowels, right, okay? And you know my sets are going to change in every problem, correct? So it get a little bit tedious, right, to think about these sets. That's why these integer segments are so useful, right, okay? So this is a good substitute, right, for the set of vowels. So a model for S, if I can, I don't know where to squeeze it in here. But a model then for S, not quite S, but something that's essentially S, right? There's a one-to-one correspondence to S, would be what I would call this set. And that means that's my notation for the set of 4 permutations from the integer segment 5, okay? Which is essentially the same as the set of 4 permutations from the set of 5 vowels. But now, in the book's notation, this means the cardinality of that set. Frequently, in my notation, I will just use that for the set itself, okay? Whose cardinality we can easily count by this theorem, right? Is that distinction clear? So what do things like this look like in that set? Just write an element for me down out of this set. A 4 permutation from the integer segment 5. Try to be creative there. 2, 3, 1, 5. Sure, right. Okay. Exactly. Just pick any 5, any 5 of the any 4 of the first 5 integers you want, right, and then put them into some order, right? Okay. So what word does that correspond to? Of course, that's what I have to think here now. E, I, A, U. Is that right? Yeah. Okay. If we think of the letters as being in alphabetical order. Now, notice that permutation, right, is not the same as this permutation, correct? Okay. Those are different permutations, because in permutations the order matters, right? But as subsets, these are the same, correct? Because they involve the same 4 digits. But as a permutation, these are not the same permutation. All right, how many of the words cannot end in U? So, still same restrictions as B here. We don't. We only want to use each vowel once, but cannot end in U. Cannot end in U. Who wants to help me with that one?
Does that just mean that instead of choosing from 5 vowels, you're choosing from 4? So instead of
No, because it can. No, because it can begin with U.
right.
It cannot end with U. Right. Okay.
Oh,
It just cannot end with U.
so
Yeah. Go ahead.
for the first 3 spaces, you're choosing from 5 vowels still, so it's 5 times 5 times 5 times 4. Because for the last placement, you have to choose from 4 vowels because you're cutting out U.
Unfortunately not, because we don't have repetition. So if I had picked you earlier in the word, right, you see what the problem is? She's saying, okay, first letter anything, second letter anything, third letter anything, but last letter I cannot pick you. So I'm down to 4 choices as I'm building the word. Okay, but that algorithm is correct as an algorithm. That's definitely correct, but you can't count it properly because you don't always know how many choices you have in the last place, right? Because if you picked U first, you would have how many in the last place? You can't use U there. Oh, is it still 4? Is she counting right? Maybe if we had picked U first, then we have 4, but if we didn't pick U first, we would still have 4.
It depends on if you're just doing it based off of that or if you're kind of continuing off of the...
Yeah, your answer might be right for how many choices we have in the last one. I was thinking not, but...
Are you saying that each vowel is still being used only once?
Yes.
Oh, okay.
Yeah.
Then should it be 5 times 4 times 3 times 1? Or...
Well, you choose the last one first like we did that one example.
Oh, yeah.
I think you do have problems because I think in the last place you're going to have a problem with U being used or not, right? Okay.
So 4 times 4 times 3 times 2.
Okay, yeah, maybe like that. All right. I had a different way of thinking about this, though. Okay, let me show you my way. I'm not saying that your algorithmic solution might be correct. I had more of a set idea in mind here. So let me go ahead and show it to you just so you will remember this is a possibility. You can also think of this through complements, okay? Right? You can also think of this through complements. So we know how many words there are all together, right? Okay? That is this set S, right? Okay? So let's make up a new name here. What do you want to call words that do end in U? U? All right, so there's words that end in U, right? Okay. Then, of course, what is U complement here? Sure, right, okay. That's the set that we're interested in, right? So if I can count U, then I'll be able to count U complement, right? Because we know what all these, what the size of all words, right, where vowels are used only once, right? That is this set S. So we know that the size of this set, the size that set that we're interested in, right, is going to be all words, right, minus this, minus the cardinality of this set, correct? Okay. So don't forget about complements. The only reason that, and this is the set that we just counted in the prior part B. Okay. Now look, the only reason that this might be a good option for handling this problem is maybe this is easy to count. Okay. So it could be that U, words that end in lowercase u, maybe that's an easier set to think about. Okay. Is that easier to think about? Oh, I think it is easier to think about, right? Okay, because if they end in U, then the last place is what? Fixed, right? Okay, so the last place is definitely U, right? So if you're going to construct a word, then you don't have to worry about the last place, right? Okay, so it's only filling in the first three letters, right, that is of interest to you. So how many choices do you have for your first letter? 4, right? Okay, how many do you have for the second? 3, and for the third one? 2, right? Okay, remember U is used in the last word, in the last letter, right? So, and you can't repeat letters. So you really have 4 times 3 times 2, correct, ways of building words that end with U. Okay. Oh, nice there, right? So, so the cardinality of U, right, is that's easy to count. That's 4 times 3 times 2. So what's the answer here? What was S? All words? Was it 120, right? Is that what we counted here? Am I looking too far back? 120 minus, what's this set? That 24? Okay. 96. So I claim it's 96. So there would be a good, there's a good problem for elementary school children. Write down all 96 words there that don't end in U. Okay. The reason I think that would be a fun problem is they're going to have to think about it kind of systematically. So getting them to think about it, you can try it too. Getting them to think about systematically about how they can construct all those words that don't end in U. That's a good puzzle. All right. Mm-hmm. Did it also end up with 96?
Yes.
Oh, okay. Well, then it's right.
4 times 3 times 2
Okay.
is still 96.
All right, good. All right, so that I just hadn't thought of that. Okay, I was probably when I was making up the problem, I was obsessed with demonstrating complements there. Okay, let's get a little bit harder application of permutations. All right, so still think permutations. So I think in most of these problems, we are using a set of permutations as a model. But again, sometimes you have to be creative, a little bit creative about how you conceive of the set from which you're going to draw the permutations. All right, so y'all know this game, right? So this is really an elementary school game. This is Mystic Square. So that's a sliding puzzle, right? With number squared tiles just like this. And it can be mounted on different size grids, but typically it's on a 4x4 grid, right? These are sliding tiles, right? So you can slide the tiles, left and right and up and down if you've got space to, right? Is shown here. And of course, the goal of the game is, starting from some random assortment of the tiles to put the tiles back in order. By the way, that game does not always have a solution. Did y'all know that? So exactly half of the initial game positions will have a solution. You can get the tiles in order from the initial game position. I thought they always had solutions. So, because you always got these puzzles like in like prizes for like McDonald's toys or something, right? Well, apparently they're cruel because half of the initial game positions don't have a solution. But our question is not that. How many initial game positions are there? So how many ways can you start the puzzle? Of course, one would be the puzzle already solved, right? So it would be 1 to 15, right, across here with the with the empty tile at the end, right? So that's one, but obviously there's a lot more, correct, including this one. I don't know if that one has a solution or not. So how many? So clearly this is a matter of arranging what?
15 numbers and 15 spaces.
Yeah, it's a matter of arranging 15. It's a matter of arranging these number tiles, right, which are essentially 15 numbers, okay? And you can think of them as, although you're not exactly arranging them left to right, you can think of them as arranging from left to right if you think of the first row as going first, right, and the second row is going second, and the third row is going third, right, and the fourth row is going fourth. So you can think of it as an ordered arrangement of the 15 tiles, which is essentially 15 numbers. So it looks like you're working with permutation of what set? 15, right, okay? Yeah, the integer segment 15. So it seems like maybe the answer is as simple as the set model here is as simple as, let's see. So let's describe this. So this S is the set of initial game positions, right? And so we're thinking maybe the model for S is just as simple as what set? So what did we describe there? The set of... well, yeah, we're starting from the integer segment 15, but what are we creating from that set of the first 15 integers? A permutation, right, okay? So how did I denote that permutation set? It's P what? Of what? 15. And how many of these integers are we lining up? Remember, this doesn't have to be 15 here, okay? This can be a number less than 15 if you're lining up fewer elements out of the set than all 15. But here we're lining up, is it all 15, right? So it looks like the 15 is going to go here. So that is... how big is that? 15 factorial over 15 minus 15 factorial, right? You subtract this number from this one in the bottom. But that's 0 factorial. And you see why we define 0 factorial? By definition, that's 1. So we get 15 factorial, right? But I know y'all are getting ready to object here, okay? But you can explain your objection. Shelby, are you going to object?
I was just going to ask a question.
Yeah, I think which I think is essentially an objection. Okay. But go ahead. I'm anticipating your question, but go ahead.
Does the open space not count?
Yeah, the open space is important, right? Okay. So we have this model is not the right model, right? Because what did we forget to take into account? Yeah, the open space. In the initial game position, the open space does not have to be in the lower right-hand corner there, okay? So the open space can be elsewhere in the initial game position. So if you're thinking in the initial game, this has to be the square that's open. No, that's in the initial game position, the open square could be in other places as well, right? Okay? So you're right, we haven't taken into account the position of the open square, okay? So Dalton, how are you thinking then?
Then just if you want to either imagine empty square is square 16.
Oh, right. So yeah. So just think of this as square 16, right? Okay. Just think of the open square as being square 16, and then what are you really arranging? Not 15 squares, but what? 16, right? Okay. So we just didn't think of our integer segment correctly, right? Okay, we really had 16 things, right, that we needed to arrange, right, instead of 15 things, because the open squares position also is important in the initial arrangement. So just change all of these, right? So you get 16 factorial. So it's you could have thought of this in a slightly different way, okay? Well, let me not go into that. All right, so this is pretty clear. Okay, so there we go. Right. Okay. Okay. You see what? See, this is this I'm thinking of as a set, but now immediately then started thinking of this as what? See, this equation is invalid. Why? Yeah, that's right. If I'm thinking of this as a set, then I can't say it's a number, right? Okay. But the book just avoids this by thinking of this as a number. But it's convenient for me to be able to think of this as a set as well. Okay. So let's be a little bit more careful here. There is the set correspondence, and now here is there's the cardinality of that set. Okay. All right. So 16 factorial. Let's make it harder. Remember, I said you don't have to play this on a 4x4 grid, okay? So let's bump it up to a 6x6 grid, but we still have 15 numbered tiles, okay? So we're not increasing the number tiles. We're going to have still the 15 tiles, okay? All right, so why is that now? You see the issue that we have run into here. Why has that now become so much harder?
Same thing as like counting one because you have multiple empty squares.
Yeah, see, now that it's the problem with the multiple empty squares. All the empty squares tend to look what? The same, right? Okay, yeah, they all tend to look alike. So my point is here that the answer is different, right? So so if you see this problem and you're thinking, oh, S, that's got to correspond to 32. No, wait, is that right? 36. Well, that's definitely wrong. But if you're thinking of this as just the permutations of 36 items, right? Okay. Kind of the 36 positions here, right? You've wildly overcounted, right? Okay. This is much more. This correspondence is not correct, right? There are a lot more things in this set than there are in this one. So, because why is that the case? Right. So I've got the numbered tiles here, right? And then I've got these blanks. So let's just put B there where we have blanks, right? So there's the, there's kind of the obvious beginning initial game position, right? Okay. You've just got the, the 15 tiles numbered, right, in the top left-hand corner, right? Okay. But if you're thinking of permuting, right, these 36 tiles, then you're assuming there in this set, right, that all of these blanks are what? Yeah, that you're assuming that they're all distinguishable, correct? Okay. So, see, Shelby, if we flip these two blanks, then that would give us a different permutation, right, in this set, correct, right? But that's still the same game board, right? Because we can't tell the difference between blank tiles, right? Okay, I mean blank squares, correct? All blank squares tend to look alike, right? So, so we've just wildly overcounted here. This would be correct if we had sort of subscripts, right, or superscripts on these on all these blanks, right? There's 21 of them, so. So if we could distinguish the blank squares, right, then this would be the correct model. That wasn't an issue in the part A of the problem, right, because there was only one blank square, so you could distinguish that one, correct, right? But now here you've got you have a real problem, right? Okay, so any ideas of how to go about fixing this? Yeah, Sean. Keep this as 36. But change this to 15. Okay. All right. So keep that as 36, but change this to 15. Okay. So so what is an element of what does an element of this set look like then? See, because now what you're going to have to do is explain to me how you take an element of this set and match that with a game position, right? Okay? Because I've got to be convinced that these two sets have the same size, all right? So what's our correspondence, right, between things in here and things in here? So just give me something out of here, but you don't have to you don't have to describe it.
Like 15 blanks?
Yeah, well, there's 15 numbered positions. Or there's 15 numbered tiles that can go anywhere on 36 spaces.
Mm-hmm.
The rest are just filled with points. So.
All right, so let's write something down. Write something down for me there. So let's put one. So just fill in a few things here in this permutation. It's kind of hard to write the permutation because these things have 2 digits in them. So I'm going to have to put commas, but normally you wouldn't put commas in a permutation, but I'm going to have to here. So what's something in here? Just give me something.
1 blank. I don't know.
Okay, no, yeah. What does this thing look like? Yeah, Chad, what does that look like?
36 is like each of the locations, so like one location.
No, you're getting a little bit ahead of yourself. I know what you're saying, but you're getting a little bit ahead of yourself. But we'll get there. But first, I just want you to say just describe for me something in this set. So again, what is this set? It's the integer segment 36, right? Okay, right? So that's 1, 2, 3, 4 up to 36. And then what do we do with that set? We take what? You take 15 numbers out of that set, and then you list them, okay? So you put them in order, all right? See how that set looks like, right? Okay, so do that for me. So you've got the integer segment 1 to 36, so take just 15 of those numbers and put them in a list. We don't have to write down all 15, but just give me a few of them, right, as kind of an example there. Well, try to get creative here, right? So the integer segment 1 to 36 is the numbers 1, 2, 3, 4 up to 36, right? We're going to take 15 out of those numbers, 1 to 36, right? And then we're going to just put them in some arrangement, some order. They can be mixed up in the order, though, right? Okay? So all you have to do here is tell me, I just want an arrangement of 15 of these numbers 1, 2, 3 up to 36. So just make up one for me. Right, yeah. So 1 is fine. Kind of boring, but that's there, yeah. So what? Okay, yeah, get wild there, get crazy. No, this could be 36, right?
27.
Yeah, this could be 27, right? Right? Because you're just picking things out of the set 1 to 36, right? And then you're just writing them down. So that can include 36, correct, right? Okay, 27, what else there? 15, 4, and blah, 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 right? Up to, what's the last one you want there? You can't pick one of the things that you've already picked, so 21. All right, so great. So, but keep in mind, how many of these things are there? 15, right? Yeah, okay, right. Great. Now, all right, so there's something in that set. Now tell me, what game position does that correspond to?
That corresponds to the numbers.
Oh, shall I erase this? Shall I erase what I already have here? Yeah, okay, so now, all right, now tell me, where am I going to put the 15 tiles? See, that's what's required, right? Because you're saying there's a correspondence between these sets, right? So if I give you something out of this set, you're supposed to be able to tell me how to arrange the tiles, right? So according to that set, how do I arrange the tiles? Oh, one would be in position 1, right, okay. Because what is that, so how do you know that from this? Yeah, what are the 36 things in this set really representing there? The 36 tiles, right? Okay. Okay. So you're saying because I took the first tile out of the 36, which I assume would be this one, right? The first square. This is not tiles. This is squares, right? There aren't 36 tiles. There are only 15 tiles, right? But there are 36 squares. So this says I took the first square, and because I put the first square in position 1, what am I going to do? I'm going to put tile 1 there. Correct, right. I'm going to put tile 1 here. Now what do I do? That's right. Okay, so this is square 3, and because it's in position 2, I'm going to put tile 2 there. So 2 goes here, right? Yeah, 2 goes here. What else now? Tile 3 goes in square 30. Y'all see that, right? Okay. So we're thinking of the positions in the permutation as representing the number of tiles, right? Okay. And then the position in the permutation is the number tile, right? And then this tells me which square is going to get that tile, right? So what gets tile 4? 27. Where is 27 on here? Okay, what was that? This one? Oh, here? Oh, okay. So that, I forgot what goes there now. That's 4, right? Okay. And what gets 5, because this is position 5. Where's tile 15 on this list? Here? All right, so that is 5, right? Okay, and then what gets 4? So 4 gets 6. 6 goes there. Is that right? Oh, backwards? So this is...
That's square 4 here.
Oh, so... Yeah, okay. So, all right. So 6 goes in square 4.
Which is right next to 2.
Oh, here.
Yeah.
Oh, I just counted wrong there. Okay. All right. Etc. Oh, finally. Oh my God. What's this one? That's the 15th one, right? Okay. So 15 goes in square 21. What is what's square 21 there? There's 18, right? 19, 20. This one? Okay. So 15 would go here. What do you do with all the... so this only tells you where the 15 number... What squares the 15 number tiles. What about all the blank ones? They're blanks, right, okay? So when you're through filling in, right, the 15 tiles, whatever's left is blank, right, okay? That's where the tile is not going to be located. Does that make sense? Ooh, wow, that was good. That was great. That required a little bit of logic. So it is a permutation set, but not exactly the initial one that you would think of, right, okay? Great. Oh, well, we're out of time. Okay, I knew those were going to be. Fun. All right. Okay. Well, we've really only got one more set model to go. So we, after permutations, we still have a few more permutation examples to look at. Okay, but there's only one more type of set model, and it's very similar to permutations. It's how do you in a permutation, right? You take elements out of a set and you put them in order. Okay, in this set model, we're just going to take elements out of the set, but we're not going to put them in order. Okay, so it's just taking a subset of a set rather than a permutation of a set. Okay, yeah. All right.
Is this correct?
We're done. So remember, the test is Wednesday. Oh, I forgot to give you your homework back. Did the roll come out? Is what now?
Is that correct because of the N and the R from what we learned in Theorem 8?
I think that is correct, right?
Mm-hmm.
Yeah. Mm-hmm. Right. All right. Michael, is Michael here? Palacios. So again, now, if the score wasn't quite what you wanted, right? Don't fret about that. Just remember on the second homework to come visit me more often, or on the third homework. You've already turned it. Sean, are you SEAN? No, you're that one, right? Okay. So is it Bradley King? Bradley? Eric? Y'all come to me. Eric? Sean? Taylor's missing. Diana? Eva? Eduardo? Kaylee? John? Chad? Shelby? Catherine? Dalton? Again, the solutions are posted. Julian? So you can find the solutions. Marion? Thanks, everyone. Yes.